Welcome to this deep dive into advanced graph theory. We are going to move beyond basic definitions to understand the algorithmic backbone of connectivity. Specifically, we will analyze how we represent graphs in memory and how those representations dictate the performance of our primary tool for exploration, breadth-first search, or BFS. We'll look at the math, the code logic, and the real-world applications.
Before we can traverse a graph, we must define how it lives inside a computer's memory. This is the structural substrate. The choice we make here, between a matrix and a list, determines the asymptotic fate of our algorithms.
We have two primary contenders. On the left, the adjacency matrix. Think of it as a rigid grid. It offers instant access to check if two specific nodes are connected, but it consumes memory equal to the square of the vertex count, usually denoted as big O of V squared. On the right, the adjacency list. This is a dynamic collection of pointers. It only stores connections that actually exist, making its memory usage proportional to V plus E. As we will see, this difference is critical for traversal.
Here is the hidden trap of the matrix. When an algorithm like BFS visits a node, it needs to find that node's neighbors. In a matrix, the algorithm is blind. It doesn't know where the neighbors are, so it must scan the entire row, checking every single column index. That costs big O of V time for every single step. Imagine trying to find your friends in a stadium by walking to every single seat to see if someone is sitting there. It is incredibly inefficient if the stadium is mostly empty.
In contrast, the adjacency list is like having a contact list on your phone. To call your friends, you simply iterate through the list. You don't dial every possible phone number in existence to see who picks up. Because we only process edges that actually exist, the total work for the entire algorithm drops to big O of V plus E. For large, sparse networks like the web or Facebook, this is the only viable option.
Now that we have chosen our data structure, the adjacency list, let's examine the engine of discovery itself, breadth-first search. BFS is defined by its strategy. It moves layer by layer. Like a ripple in a pond, it visits everything at distance 1, then everything at distance 2, and so on. This concentric expansion is what makes it mathematically optimal for unweighted graphs. The mechanics rely on a queue, a first-in, first-out structure. We start by enqueuing the source node. Then we enter a loop. We dequeue the current node, look at its neighbors, and if they haven't been seen before, we discover them by marking them as gray, meaning visited, and adding them to the queue. This cycle repeats until the queue is empty. This rigid ordering guarantees we never process a node at distance k plus 1 before finishing distance k.
There is a critical implementation detail that trips up many engineers. You must mark a node as visited the moment you see it and add it to the queue. If you wait until you pull it out of the queue to mark it, neighbors will add the same node multiple times. In a dense graph, this causes quadratic redundancy, specifically big O of V.
Why do we trust BFS? Because it is provably correct. By induction, we can show that if BFS has correctly found all nodes at distance k, it will correctly find all nodes at distance k plus 1. A key invariant is queue monotonicity. The distances of nodes in the queue never decrease and differ by at most 1. This ensures the algorithm never jumps ahead, guaranteeing the shortest path in unweighted environments.
However, BFS is not a silver bullet. Its optimality collapses the moment we introduce edge weights. BFS assumes one hop equals 1 unit of cost. If you have a graph where one road takes 10 minutes and another takes 1 minute, BFS will choose the path with fewer segments, even if that path takes 10 hours. For weighted graphs, we must upgrade to Dijkstra's algorithm.
For complex problems, we use advanced variations. Bidirectional BFS runs two searches simultaneously, one from the start and one from the target, meeting in the middle. This can reduce the search space from a massive sphere to two much smaller spheres. Another brilliant variant is 0-1 BFS. If edge weights are only 0 or 1, we can use a double-ended queue instead of a priority queue, pushing 0 cost edges to the front and 1 cost edges to the back. This restores our linear time complexity. Finally, we compare BFS to depth-first search. While BFS explores layer by layer to find the shortest path, DFS dives deep along a single branch. On finite graphs, both algorithms are complete, meaning they will eventually visit every reachable node. However, their memory profiles differ. BFS can be memory-intensive, as it stores the entire wide frontier in the queue. DFS is typically more efficient, as its stack scales with depth, though both must track visited nodes to avoid cycles.
BFS isn't just theory, it's a workhorse in the real world. For example, it's the core principle for finding the path with the minimum number of hops in a network. While major internet routing protocols like OSPF use more advanced algorithms like Dijkstra's to handle variable link costs, BFS is perfect for the unweighted hop count problem. It's also used in copying garbage collectors to traverse live memory objects, and by social networks to calculate degrees of connection, like finding friends of friends. It's a fundamental building block of modern computation.